the design example. So in this one, we are looking at two walls. One is 5 meters of length. The other one is 7.5 meters of length. 7 meters of length. Coupling beam is 700 deep, 250 millimeter thickness. If you want, you also can just draw a sketch of this information so that you will be able to follow what you are going to do. Is it okay? Can you all just make a sketch of what you are discussing? So we are talking about two walls aligned, 5 meters and 7 meters of length, connected by a coupling beam of 700 millimeter depth. Generally the width of the coupling beam will be the same as the width of the wall, and the length of the coupling beam is 2.5 meters. So from this you can work out what is L. L is equal to 5 divided by 2 plus 2.5 plus 7 divided by 2. 3.5, 4, 6, 8.5 meters. And the floor to floor height is 3.2 meters. Okay. So basically the arrangement is that we have two shear walls like this, 5 meters, 7 meters, 2.5 meter gap. So L is 8.5 meters. And these walls are arranged like this at a spacing of 6.25 meters. So the idea is having one apartment here. These are not real big apartments, very small flatlet type apartments. That means you get a small living area, a bedroom, and a pantry, and a bathroom, so or a washroom. So all in one unit, small units. Especially for single people and all that. So that's a type of building that we are considering, having 20 floors. And again, a slightly large apartment on the other side. So this is 5 meters by 6 meters, which means 30 square meters, which is a small apartment. And a slightly bigger one on this side, 7 meters by 6 meters. And there's a passage of 2.5 meters in the middle. And these walls are connected by using a coupling beam. And the building is having 20 floors. 20 floors. And the floor to floor height is 3.2 meters, giving a total height of H of this simple H, 64 meters. So that's the information available up to now. And we look at more information now. And there's a floor slab of 200 millimeter thickness. Floor slab of 200 millimeter thickness. Allowance of floor slab 200 millimeters. And allowance for finishers 1 kilonewtons per meter squared finishers, and 0.5 services, and again 1.0 for partitions. And we consider that there's an edge beam or something that will, sorry, this is not only internal partitions. Basically, it will take account of all the walls, because these external walls will have windows, whereas lightweight material can be used to separate the apartment from the corridor. So the partition material will be lightweight material. When I say lightweight material, it can be masonry, but it's lightweight. And the external wall will have windows. So because of that reason, we'll consider this 1 kilonewton per meter squared would allow for all those partitions. Because when you allocate 1 kilonewton per meter squared over 30 square meters, we are allocating 30 kilonewtons, and that could be sufficient to look after the weight of most of the partitions if they are lightweight. If they are heavy, then we have to consider those the weight of those partitions separately. But here we consider this 1 kilonewton per meter square looks after everything. Right? We consider this 1 kilonewton per meter square looks after everything, just to keep things simple. And the live load of 2 kilonewtons per meter squared. Generally, the apartments are designed for live load of 1.5 kilonewtons per meter squared. But the passage is designed for a live load of 3 kilonewtons per meter squared. But here we consider that everywhere it's 2 kilonewtons per meter squared, just to keep the calculations simple. But you can consider the fact that the live load can be different in the passage and the apartment. So basically, this is the information that we have. And the first question is, determine the dead and imposed loads acting on the flow slabs. Determine the dead and imposed loads acting on the flow slabs. So first we'll do this calculation. Determine the dead and imposed loads acting on the walls transferred from the slabs. So the slab thickness is 0.2 meters. 0.2 into 25 is answer is 5 kilonewtons per meter squared. That is the slab dead. Then finishers 1, services 0.5, partitions 1.0. That gives a total of 7.5 kilonewtons per 7.5 kilonewtons per meter squared. So then we have to see how much load is actually transferred onto each wall. So we have two walls, 7 meters, 5 meters, separated by 2.5 meters. So we consider that the load on this area, we'll act here. So load on 6.25 meters will act on this wall. So load over 6.25 meters will act on this wall. So we can say the total load transferred onto the wall at each floor level, at a floor, dead, is equal to 6.0 multiplied by 6.25 multiplied by 7.5 divided by 5, and that will give us the load acting on the wall. 6 multiplied by 6.25, that will give us the total area multiplied by 7.5 will give us the full load, divided by 5 will give us how much load is acting over 1 meter length. How much load is acting over 1 meter length. So that is wall 1. And on wall 2, we get 6 into, here you get 8.25 multiplied by 7.5 divided by 7. And again you will get 6 into 8.25 multiplied by 7.5 divided by 7. 53 not kilonewtons per meter. So we get, you can find the load acting on each wall. So similarly, we can do the calculation for live loads. Live is 6 multiplied by 6.25 multiplied by 2 divided by 5. So here you get 6 into 6.25 multiplied by 2 divided by 5. So you get 15. And live on wall 1. On wall 2, you get the answer as 6 into 8.25 multiplied by 2 divided by 7, 14.14 kilonewtons per meter. So these are the loads acting on the wall. So that is the first part of the problem. We have been asked to find the loads acting on the wall. Dead and imposed loads acting on the wall. Dead and imposed loads. But what you have to keep in mind is, in addition to these loads transferred at each floor level, we have to consider the self weight of the wall as well. Self weight of the wall as well. So this information we'll keep aside for the time being. Then we have been asked to find second moment of area of walls and connecting beams. Right. So we'll see. We have two walls, 5 meters, 7 meters, bending above this axis. I1, 1/12, B, D squared, D cubed, I2, 1/12, 0.25, 7 cubed. So the answers are 2.60, and this one 7.14. So you can find the second amount of area, I1 and I2, and I2 is also found about this. And connecting beam, 1/12, And that's a small value, 0.00715. Zero 0715. So that's the second part of the problem. Then say determine the structural parameters K alpha and K alpha H. So we have been asked to find K alpha, K alpha H. So we'll find first we'll find K squared, which is given by 1 plus AI over A1 A2 L squared. So you can just take down these two expressions. Alpha squared is equal to 12I connecting beam L squared divided by B cubed HI, B cubed HI, and K squared is given by K squared is equal to 1 plus AI over A1 A2 L squared. And alpha squared is given by 12 IC L squared over B cubed H. So there are two equations, and we are going to find K alpha H. So these are the two equations for this, and I is equal to I1 plus I2, which is 2.6 plus 7.14, 9.74 meters to the power 4, and area A1 is 5 into 0.25, 1.25, A2 7 into 0.25, 1.75. Capital A is equal to A1 plus A2 is equal to 3 meters squared. And L is 8.5 meters. Earlier we found it. L is 8.5 meters. 8.5 meters. L is 8.5 meters. We earlier found it. L is 8.5 meters. And B is 2.5 meters. So you can find K squared. K squared is AI 3 into 9.74 divided by 1.75 divided by 1.25 divided by 8.5 squared plus 1. 1.18, you can find K as well. 1.08. Similarly, we can find alpha squared. 12 IC connecting beam 0.00715 multiplied by L squared 8.5 squared divided by 2.5 cubed. Height is 3.2 and I is 9.74. And this gives 12 into 0.00715 multiplied by 8.5 squared divided by 2.5 cubed divided by 3.2 divided by 9.74. 0.0012 0.0127 0.127 alpha square root of that 0.112 alpha is 0.112. Is it correct? Twelve into 0.00715 multiplied by 8.5 squared divided by 2.5 cubed divided by 3.2 divided by 9.74. 0.0127 square root of that 0.112. Is it correct?
Yes, sir.
It's correct. Now we know alpha squared alpha. So now we have to find K alpha H. 1.08 112 multiplied by height 60 gives 1.08 into 0.112 into 64. 7.74. Right. Here you can see now K alpha H is 7.74, which is a fairly high value. So if K alpha H is about 3 or 4, then it's a reasonable value. K alpha H is 7.4, 7.74. The reason is we are having a coupling beam of depth 700 millimeters. So flow to flow height is 3.2 meters. 3.2 minus 0.7 gives 3.2 minus 0.7 gives 2.5 meters, the opening height or the passage opening height. And so you can see we are having a fairly rigid beam connecting because 0.7 meter depth over 2.5 meter span. So we are having a fairly rigid beam. So that's why we are getting 7.74. So what you have to see is, value of 3 or 4 are reasonable for K alpha H, and we are having a slightly higher value because we are having a fairly rigid connection. So that is just mechanically done just to find the values. Now we are coming to the important part. Now the next question, if the walls are acting independently, determine the bending moment resisted by each wall at the ground floor level. So this fourth question is no coupling action. No coupling action. This is no coupling action. Find the bending moment carried by each wall. No coupling action. Find the bending moment carried by each wall. So find the bending moment carried by each wall. So we have two walls. 6 over a height of 64. So capital M is equal to W H squared divided by 2. So which is given by 64 squared divided by 2. 6 into 64 squared divided by 2 gives us 12,288 kilonewtons. Now you can see the effect of lateral loads. Over 64 meters, the moment due to lateral loads is 12,288. You can see it's a fairly high bending moment, 12,288. It's a fairly high bending moment, and it acts over this acts on these two walls. Then how do we determine M1? M1 is equal to I1 over I1 plus I2 times M. And so M1 is equal to I1 is 2.6. I1 plus I2 is 9.74 multiplied by 12,288. So you get 2.6 divided by 9.74 multiplied by 12,288, and you get 2,280, 3,280 as the bending moment carried by 3,280 kilonewton meters being carried by as M1, and M2 is 7.14 divided by 9.74 multiplied by 12,888. That is a safer way of calculating these values. Otherwise, you can just deduct 3,280 from 12,288. So you get M2 as 9,008 or 9,007 kilonewton meters. So that is the fourth part of the problem. If the walls are acting independently, find the bending moment on each wall. Is this clear? Finding the bending moment on each wall. Right. So now we look at the next part of the problem. Hence, determine the vertical loads acting at the ground level, and then determine the stress distribution that could occur under each wall. So we are asked to find the stress distribution under each wall. And the first question is determine the vertical loads acting at the ground level. Determine the vertical loads acting at the ground level. So first we'll answer that question. Determine the vertical loads acting at the ground level. That is the next question. You have to find the vertical loads acting at the ground level. So we have to look at few things. What are the loads that are acting at the ground level when you have a wall like this? At each floor level, we get loads acting downwards. That is all due to dead loads. Then in addition to that, we get the self weight of the wall. Self weight. So we have already calculated the dead and live loads for wall 1 and wall 2. Permanent loads. We calculated that 56.25 and 53 kilonewtons per meter, and self weight is 0.25 multiplied by 64 multiplied by 25. That is, self-weight is 0.25 multiplied by 64 multiplied by 25. Self-weight is 400 kilonewtons per meter, and this has to be multiplied by 20 because there are 20 floors, and we will consider the roof also transfer the same load. So you get 56.25 multiplied by 20, 1125, and on this side you get 53 multiplied by 20, 1060. 1060, and self-weight is the same, 400 kilonewtons per meter, and the live load is 15 multiplied by 20, and here the live load is 14.14 multiplied by 20. We calculated these values earlier. If you go through the video, you can see 15 into 20, 300 kilonewtons per meter, and on this side you get 14.14 multiplied by 20, 20 floors, 282. So these are the dead and live loads, permanent loads and variable loads. Now we come to the very important. Now we come to the very important aspect, and that is to find the stresses. So if you take the wall number 1, we have a moment M due to the wind. We have the axial load dead, that is permanent, and then we have live, variable, and this is also variable load. So if you look at Eurocode 1, the combinations are given there. So we can have these combinations. The first combination is when you have a wall, we have W, what is the most critical situation for this wall? This wall carries no live load, and wind is maximum. So it is represented by 1.0 GK plus 1.5 W. So what happens? Minimum dead load will give a stress distribution like this, and compression, this will be like this, wind, and there's a possibility that we'll end up with something like this, where we get tension. And tension here can uplift the foundation. Tension here can uplift the foundation. So this is one of the critical cases that we have to consider. So we call it combination number 1. What are the other cases? The other case is we have no wind. We get 1.35 GK, 1.5 QK. No wind. That's another case. What are the other possible cases? Then it's possible for wind to act as maximum Wk, and we call it 1.5 times Wk, and the dead load is also maximum 1.35 Gk. So what happens? We get the maximum compression here. We can get maximum compression here. But because Gk is with 1.35, the chances of tension occurring here is remote. So for tension case, we have to consider this one. For maximum compression, we have to consider that. But at the same time, we can have another case, and that is wind is maximum. So wind is the primary variable load. Dead load is 1.35 Gk, and then we like to have Qk. So what is the parameter? What is the factor that we get for Qk? So this should be 0.7 into 1.5. So we get 1.05 Qk. The reason is we can't have two primaries, so this will be secondary, which means we have to multiply the imposed load by 0.7 to get this effect. Then the next one is the dead end imposed will become permanent and primary, and the other one becomes others. So you get 1.35 Gk. Here you get 1.5 times Qk. What happens to the wind? Wind is 0.5 times 1.5 Wk, which gives 0.75 Wk. Is that clear? So these are the load combinations that we have to consider. And what do you get in this one? This one also you get maximum compression here. Here also you will get maximum compression. Is that clear? In Eurocodes you get these variable actions and permanent actions. For variable actions, at a given time we will have one primary variable action, others will be secondary. And for wind, when it is primary, it's 1.5. When it is secondary, it is 50% of 1.5. For live loads, it's 1.5 when it's primary. When it's secondary, it's 70% of 1.5. 70% of 1.5 is 1.05. Is that clear? So now we look at what happens with these cases, because I'm going to compare the results that we get without coupling and with coupling actions to show you the beneficial effect of coupling action.